So here we have this marble of mass m is compressed against a spring with spring constant k and released. It travels around a loop of radius r. Sorry, I'm just going to make that a little bit bigger. Assume the size of the marble is small compared to the loop and that there's negligible friction on the track. What is the minimum speed that the marble needs to travel to make it through the top of the loop while keeping in contact with the track? So it's the minimum speed. So the hint is to draw a free body diagram up here. So where the marble is going to go through here, it's going to come to this loop here. And now what forces are acting on it? Well, we have gravity acting downwards towards the center of the object. And the track is above it, so the normal force, it's exerting a pushing normal force downward as well. So that's step one. This is our forces analysis. We draw the free body diagram, right? So we have gravity acting downwards. And we have a normal force also acting downwards here. Okay, so they're both acting in the downward direction. 2, identify the acceleration. Now, it's moving in a circle. So that means, so it doesn't need to have velocity 0. If the velocity 0 just falls, I want it to go in a circle. So it's moving in a circle, so there's centripetal acceleration down towards the center of the circle. And that means we're going to make positive next directions, and then we're going to do F net equals ma. We don't need to decompose any forces, not on inclined plane or anything like that, so we're just going to do F net equals ma. That is Fn plus mg equals m times the centripetal acceleration, which is v squared over r. Now here's the thing. We want it to keep in contact with the track, but we want the minimum speed, right? What's the minimum speed? So let's solve for v. We're going to solve for, it's going to be r times Fn plus mg over m. Square root of that is going to give us our speed. All right, that's the speed. Now what happens is as you go faster around, what's going to change? Well, the r of the loop can't change. It's the fixed track. We're not breaking the track. The mass doesn't change. D doesn't change. Fn is the only thing that change. As you move faster, right? So what's the minimum? The smallest Fn can be is equal to 0. The smaller Fn is, the smaller the velocity is going to be, right? So if we're just barely keeping contact with the track, is the Fn is just barely there, like very, very close to 0. So if we do that, if the Fn is going to 0, then the velocity is going to be square root of r mg over m, which is actually equal to the square root of rg, because the m's cancel. So that's part A. Okay? Those are the steps. That's our analysis. We draw the free body diagram. We identify the acceleration. We apply F net equals ma. And then we have to interpret what the results are, what our analysis is telling us there. So now it's what is the compression needed for the marble to have the speed at the top of the loop? Now, what's our process? This is going to be an energy kind of analysis because there's all kinds of stuff. There's all kinds of different motion that's happening in here. However, let's think about our system. So first is what's the system? The system is going to be the marble. Because there's a change in height, we're going to include the earth. And because there's a spring, we're going to include the spring. Okay? So after we identify the system, we draw a free body diagram. We kind of already did the free body diagram for parts of it, but think about it just in general. You're going to have gravity. You're going to have a normal force. You're going to have maybe a spring force. And sometimes over here, the normal force may be perpendicular to it, but whatever. Like during the motion, you have different forces. However, basically, none of the forces do any work. Normal force doesn't do any work. Work by the normal force is 0. Spring force internal to the system doesn't do any work. Gravity internal to the system doesn't do any work. So ultimately, so we draw the free body diagram. Now in this, determine what the work is. The work is 0. None of the forces do work. Okay? Forces are either internal or Fn is perpendicular to the displacement. Right? What's the initial energy? Well, what's the energy at the start of the motion here is we've released it from rest, so the velocity is 0 down here. So if we think about the 3 forms of energy, we have kinetic energy, gravitational potential energy, and spring potential energy. We have all 3 forms of energy here. Now, for kinetic energy, this is 0 because it's not moving. For gravitational potential energy, you'll make the ground, the lowest point of the motion, make that h equals 0. So there's no gravitational potential energy. There's just some spring potential energy. It's 1/2 kx squared. Okay. What is the final energy? Well, at the top of the loop here, we have some velocity, right? So in terms of what energies do we have? We just go through one at a time and think about it. Do we have some kinetic energy? We absolutely do. Because up here, we said it's moving with v square root of rg, so that's square root of rg squared. How about gravitational potential energy? Are we above our reference height of h equals 0? We absolutely are. And the height is actually 2r, twice the radius of the circle, so it's 2r there. And then, is the spring compressed at all? Well, now that we've relaxed it, right, it's released, at the end, we assume the spring is now, it's now at its relaxed length, because nothing is holding it in place. It's now back to its relaxed length. That's 0, right? So the spring is relaxed. So that is going to be 0. So then our final energy is going to be 1/2 mRg, because the square and the square just gets rid of it, plus 2 mgr. And so that's going to be 2 plus 1/2 is 5/2 mgr. And now we're going to do work is the change in energy. So the work was 0. The final energy was 5/2 mgr. The initial energy was 1/2 kx squared. And we want to solve for x. So that means 1/2 kx squared is equal to 5/2 mgr. Okay, 2's cancel. You can get x squared is equal to 5 mgr over k. And so x is equal to the square root of 5 mgr over k.